find instructions like jump EBP. Where do we find such an instruction? We go looking through some binaries. We go looking through basically this dark blue region on the top, the code, where our compiled code is, or where shared libraries may be loaded. This code and shared libraries are loaded at pretty much fixed offsets in most, without loss of generality. So what you do is you go looking through one of these libraries and find out a suitable instruction, say a call EBP or a jump EBP instruction. In this example, I've used user32.dll, which is one of the popular Windows DLLs that gets loaded with every Windows process. The address of call EBP in the DLL is going to be constant. So what you do is you populate your overwritten EIP with the address of that instruction. Then when the function returns, EIP is going to be popped off, control is going to be transferred to that particular instruction within the DLL, and then that instruction is going to say call EBP, well, EBP was already pointing to where your shellcode is, and voila, you get execution of shellcode. So these are some of the mechanics of how we can construct an exploit. The last part needs to be solved is where do you get the shellcode from. Okay, so now let me jump into some demos. I have a program called PeerCast, which is like a peer-to-peer streaming thing on Linux. It has an HTTP interface and it's prone to a buffer overflow. So let me show you how we can make this error situation come up and try to create an exploit for this. Okay. Now let's see how this is going to work. Let me first log into the vulnerable system and increase the fonts for our sake. Can anybody read this all the way at the back? Okay, good. Well, now, thanks to the non-mirrored displays, I will have to struggle around. All right. It's impossible. How do I stand and type with one hand? I'm not in the habit of typing with one hand either. All right. Okay. So here I have a PeerCast. Okay, I'm going to yell. So here I have PeerCast. Is this working or? Yeah. Okay, cool. I'm going to start it up. User local PeerCast. It just starts up the binary. It's listening on port 7144, and so that's on the target system. From my attack system, okay, let me see what I got. I got a file called aaa.txt, which pretty much throws a whole set of A's against PeerCast. We just want to see quickly how this error kicks in. So say cat aaa.txt, pipe to the tool that no hacker should be without, and pipe it to port 7144. All right. And how do I keep an eye on this window at the same time? It's impossible. It's all right. Then bleed through and anyways. Here it is. It got sent and wait a minute. Wait, it's running in the wrong port, sorry. It's running on port 17,000 in my case. Okay, There it goes, and in this other window, we get segmentation fault. Let's now look at the segmentation fault. Let's now try to analyze what happened here. So I'm going to say ls. I have a core file, core.1472, say gdb target core.1472. If there's a typo, please tell me. Okay, no. Okay, here we get where it said program died with a segmentation fault. Let me say info registers. Sure enough, we have EIP as 41414141. Woohoo. Now, let's try to see where our buffer is in the memory. Maybe we can do it the systematic way, or we can do it the donkey way. I will do it the donkey way. Let's just start dumping memory pointed to by one of these registers, and maybe we'll just get lucky. The good registers look like EDX, EBX. No, EDX is in the code. EBX and ESP seem to be good choices. The rest of the ones are botched up. Okay, so I say x64 EBX. Sorry, $EBX. Okay, I get some part of the buffer. Doesn't look, I mean, some part of the memory doesn't look interesting. Say DB, x64 ESP. ESP points to some region of my buffer. Where in the region, I don't know, but looks like it's towards the very end. Now, how do we calculate which of these 4 bytes went into EIP, and how do we calculate which region does ESP point to? Well, we can use one of Metasploit's pattern generator libraries to generate a cyclic pattern. I'll not get into the details of that library right now, but what Metasploit can do for us is generate a pattern called something like this. It'll generate a cyclic pattern of alphabets and numbers such that no 4 bytes repeat themselves anywhere. Now, depending on which 4 bytes get copied into EIP and which 4 bytes appear at the location of ESP, we can find out our offsets. So let me just go and run this against Peercast and show you where the offsets come to. Okay. So let me restart Peercast. Peercast is restarted, and here let me say cat pattern.txt pipe to netcat 192.168.7.177 port 17. Typo, too many 7s. School? Okay, so we pipe it to this and get another core dump. Okay, it's listed as core.1506. So I'll say gdb target core.1506. Okay, and now we're getting some different values. Let me say info registers, and we get a value EIP as 42306142. 42306142 is something like what? B0 small a and b. Yeah. Okay, but in reverse order. Now we just try to look for this string in the pattern and find out the offset. Okay, so let me go ahead and do that. Okay, so I'm going to use one of Metasploit's pattern matchers. there's a file called SDK pattern offset.pl, and we're going to load it up with the value that we saw here. Bless you. If 42306142, 423, no, not here. 423064142, and we're going to search for it within like 1,000 byte range. When we do this, we get the number 780. This means that EIP is overwritten after 780 bytes into the buffer. So if we create a buffer with first 780 bytes with junk, the next 4 bytes will get overwritten into EIP. So now we know where to pack these bytes in. Let us now look at the region of memory that ESP points to. So we go back to GDB and say x64 $ESP. Oops. Sorry, x/64. Okay. And ESP points to 61423161. Okay. Let's run this again. 61423161. Was that right? Yeah. And ESP points to 784, which is the next 4 bytes after where EIP was saved. Okay, so this is interesting. Now what we need to do is just create a sample exploit, plug in those values, and then we're good to go. Okay. So what we're going to do is we're going to create a 1,000 byte payload. The first 780 bytes can be AAAA, anything. The next 4 bytes will be stuff that's going to be overwritten into EIP. And then we will pack our shellcode at the very end, as shown in the last diagram. Lastly, we're going to figure out a jump ESP instruction somewhere. Where do we grab this jump ESP instruction from? One of the shared libraries, or we'll try to pull it off from the peercast binary itself. Okay, and then we're good to go. Last we need is shellcode. For now, I don't know how to write shellcode in assembly. I'm going to use Metasploit to get shellcode for me. But for testing purposes, my shellcode is going to be interrupt 3, which is trap back to debugger. So if I manage to send my buffers, and on the other side I get peercast trapping back to debugger, I know that I've succeeded in my proof of concept. Okay, so that's shellcode, blah, blah, blah. We don't really care. Let me not get into all this theory stuff. Let me just show you how to do this. Okay. So let me walk you through a couple of files that I have. So come back to demo peercast. There's a sample code that I've written called peercast1.pl, which is pretty much creates the exploit. It basically assembles a GET request, the kind which causes peercast to blow up. Then you have a pad of 780 bytes. Then you